Okay. What is the integral of x minus 1 over 4x squared minus 4x plus 3? So if you want to factor the denominator, the one thing that you should always check is to see if this denominator has a 0. If it has a 0, for example, if you're dealing with x squared minus 6x plus 1, ask yourself, does this have a 0? If it has a 0, that means you can factor it. So how do you do? You can calculate through quadratic. You say 6 plus or minus square root of 36 minus 4ac, so minus 4 divided by 2a, which is 1. So in this case, this has two solutions. One is 6 plus or minus square root of 32 divided by 2, whatever this number. That means you can factor this denominator as x minus, call this, let me write this, 3 plus or minus square root of 32 is 8 times 4, so this is 8. So I can write this x minus 3 plus root 8, x minus 3 minus root 8. If you do this multiplication, you'll end up with, sorry, not with this, with exactly that. So if that term is in the denominator, you can still factor it, even though the factors are not that neat, but you can do substitution. There would be 1 divided by this, 1 divided by that, and if you're integrating, simply they use substitution again. Okay, so the only case when you know that there is no way to factor it is if you do quadratic formula and you end up with no solution or complex solutions. So if you look at this denominator, 4x squared minus 4x plus 3, set it equal to 0, and say, okay, what is the solution? X must be minus b, which is 4 plus or minus square root of b squared, 16, minus 4 times 4, 16 times 3. So it would be something like 48, divided by 2, divided by 8. You notice that under the square root, this is a negative number. It's less than 0, which means this has complex solution. So there is no real solution to this equation. That means you cannot factor this denominator. That's what it means. Okay, so what do? We try to write this integral in a form where the denominator is squared plus some other term squared. This is the whole goal. So I'm going to focus on how do I write 4x squared minus 4x. Actually, maybe I can scroll down a bit more. I'm going to focus on first, how can I write 4x squared minus 4x plus 3? It was plus 3. In terms of a factor squared plus some constant, whatever that constant is. Okay. First, you look at the coefficient of x squared. You take a square root of that. Square root of 4x squared is 2x. Because if you square 2x squared, you get exactly 4x squared. Then you would say, okay, 2x squared, I need to get this term that contains negative 4x. What if I pick negative 2? Does that help? Not really, because if you write 2x minus 2 squared, that is 2x squared minus, why do I write it this way? Let me write it this way so you can all see what the steps are when you're doing square. This term times that, this term times that, this one times that. So you'll get this 2x squared, 4x squared simply, but the combination that you're multiplying is these two and these two to get a term containing x, which is exactly the same terms. You multiply negative 2 by 2x, negative 2 by 2x. So you get a negative 4x, then again another negative 4x. So what we only care about is half of negative b divided by 2a. So negative b divided by a. So if you divide these two, if you say a is that, and this is b, if you divide them together, you'll get this constant, negative 1. That is in the case sorry, not this, if you divide by this constant 2. If you divide, let me write this, this is a, b, and c. Square root of a shows up here. That constant that you're looking for is b divided by this number and then divided by 2. So this -4 divided by 2 will give you -2. Then you have to divide it again because you're repeating the same number over and over, twice. So you'll get -1. And the case C is you need to calculate, what if I square this factor, what do I get? I'll end up with, so let me write up here. What if I factor 2x minus 1 squared? Minus 1 squared. You should end up with 4x squared minus 4x, exactly the first two match. Then you would have plus 1. But what we need is plus 3. So we already have a plus 1. We just need to add a positive 2. That positive 2 is where we need it here. Is where this fills up this box. Okay. It needs quite practice to guess that number, but if you write it down, you can always figure it out. Okay, so I can write this factor actually in a form of 2x minus 1 squared plus something squared. What is that something here? It is square root of 2 squared. It's not only 2 squared, it is the 2 that we want to write it in terms of something squared. And I'm going to write this root 2 squared. They're exactly the same thing. Okay, if I do that, then the numerator is still x minus 1. Okay, now you can do substitution. First, let's make it easier. I'm going to write u equals 2x minus 1 inside this parentheses. What is du? Du would be 2dx. So I will get x minus 1 divided by u squared plus 2 or square root of 2 squared. Okay, let me write it 2 for the moment. Du divided by 2. Because dx is du divided by 2. So now, if you notice, we still have an x here. We didn't get rid of all the x, so maybe the substitution was an issue. But you can kind of solve for x through the first equation. U plus 1 equals 2x. So what is x? It's u plus 1 divided by 2. So you can write this integral as u plus 1 divided by 2 minus 1 divided by u squared plus 2 du over 2. It is too much work, I understand that, but the steps will be always the same. You'll always do these steps. So, what did I end up with? I ended up with is this integral. You can simplify the numerator. U plus 1 over 2 minus 1 is simply u minus 1 over 2. If you do common denominator, then it divides by u squared plus 2 times du over 2. You can cancel out some of these. You can factor out the 1/2 here from this guy. You can factor it out and write it outside. So it would be 1/2. And you can put this 2 outside again. So you get 1/4 times the integral of u minus 1 divided by u squared plus 2 du. Okay, so now at this point, let me continue here. Okay, at this point, you notice that if you wanted to integrate this integral, if the numerator was simply 1, then we could have used that tangent identity. But what if there's u minus 1? What do you do in that case? In those cases, you always try to separate them. So what you do is you keep the u, and you'd have u squared plus 2, and you take out the constants. So you write this minus 1 divided by u squared plus 2 du. You can write them as two separate integrals, du minus that integral. So I separated the numerator, and I still have the 1/4, by the way, times 1/4 outside. Okay, so here the 1/4 is still there. I'm going to keep that. So calculate each of these integrals separately. I'm going to do that. What is the integral of u divided by u squared plus 2 du? That is simply, if you do a substitution again, let's say I'll let u squared plus 2 equals v or something. V equals that, and d of v would be 2u d of u. So instead of dv over 2u, I have d. So I can write this integral as integral of, instead of the denominator I have v. Instead of the numerator, which is u, I can write, let's keep the u. Instead of the du, I can write dv divided by 2u. And these will cancel out. So I ended up with the integral of 1/2 times 1 over v dv, which is simply 1/2 ln absolute value of v. You could have skipped over some steps if you're familiar with this, but I wanted to go to very basic. So what is the 1/2 ln of absolute value of v? It is 1/2 ln of, what is v? V was u squared plus 2. So this first integral became 1/2 ln of absolute value of u squared plus 2. How about the second integral? This is where we can use the tan inverse property. Here. What is the integral of 1 divided by x squared plus a squared dx? If it's u, it's still the same idea. It would be 1 over a tan inverse of x over a. But in this case, our a is not something simple. This is not supposed to be 2. You should look at this as something squared, because that formula is for some constant square root of 2 squared. So this integral becomes 1 over root 2 tan inverse of u divided by square root of 2. So finally, I have this integral as 1/4 times 1/2 is 1/8 absolute value of u squared plus 2 minus 1/4 times the second one, so it would be 1 over 4 root 2 tan inverse of u over 2 plus constancy. You may ask, are we done finally? And the answer would be not yet, because all this, if we assume our variable were u, we have u here involved. So what is the answer to this integral? It contains x, so the answer would be, go back to the substitution that you used for u, replace it with x. To be honest, I picked the maybe most difficult question because I wanted to combine all those information that we have. That's why it takes so long. So this integral, I'm going to call it star. Finally, we have the answer to the star. Star equals 1 over 8 ln absolute value of, instead of u, we had 2x minus 1. So it would be 2x minus 1. I'm replacing it into this equation because we found the integral. Squared plus 2 minus 1 over 4 square root of 2 tan inverse of 2x minus 1 over 2 plus some over square root of 2. I think this is supposed to be square root of 2 plus some constancy. Okay, so this is combined both if you have a constant or if you have a term that contains variable x or u. Then what you do is you kind of break them up. You use the one that has constant in the numerator with the tan inverse, the other one simple substitution will help. Okay, I know it's a bit too much, but try to look into the book. The book, I think, has other examples as well. Okay, so this is the case if the denominator is quadratic and the numerator is, you assume it's in terms of ax plus b. You have to figure out what is a and b. In this case, we didn't really need to figure out a and b because it was already in the simplified version and we couldn't calculate. But sometimes that's not the case. You have to figure out what are a and b. And instead of the denominator being simply quadratic, it would be quadratic to some power. So what you need to do is still do that partial fractioning plus the integration. So here is an example. As I say, if the denominator is quadratic with some power r, whatever that power is. In our example that I have is some quadratic to the power 2. That means you need to consider all those cases where the denominator is simply quadratic, or it is quadratic to the second power, or quadratic to the third power, up to the given degree. So here the given degree is 2. So I'm going to go up to second degree. And in the numerator, I have to assume that the numerators are linear, 1 degree less. Some constant times x plus a constant, some other constant times x plus another constant. So what I'm going to do is, I'm going to say numerator is given x cubed plus x squared plus 1 divided by x squared plus 1 squared. And I try to use partial fraction. How do I do that? I assume that I can write the denominator as x squared plus 1 and x squared plus 1 squared, where this term is ax plus b, the other one is some other constant times x plus some other constant d. The numerators, you assume they're linear because the denominator is quadratic, 1 degree less would be linear. In the very early examples, we assumed the denominator was linear, then the numerator is quadratic. We cannot factor out x squared plus 1 anymore. That's why I didn't think about simplifying this denominator anymore. It's not possible to factor x squared plus 1. That's why we leave it as it is. So now the question is, what are a, b, c, and d? And the technique would be exactly the same. You do common denominator. You say this equals to, do common denominator for the first fraction. That means you need to multiply the first one by itself, x squared plus 1, to get x squared plus 1 squared. And the second one already has the common denominator. So let me write this. I need to multiply ax plus b in the first fraction by x squared plus 1. And the second one, denominator is exactly the same thing. You don't need to multiply anything because it's the same as x squared plus 1 squared. So I have cx plus d here. Okay, let's distribute the numerators and write it as one function, one fraction. So what we have in the denominator is x squared plus 1 squared, and the numerator would be ax cubed plus bx squared. Distribute these. That times this times that, and so on. And I'm trying to write them in order, plus ax plus b. And you have plus cx plus d. Write the two fractions together. So you would have x squared plus 1 squared, the numerator. Which terms contain x cubed? It's only this term. Which term contains x squared? It's only this one. Terms containing x would be these two, so you get to write them together, and the leftover are our constants. So I'm going to write them as ax cubed. This is the only term containing x cubed. The only term containing x squared is bx squared. The only term containing x would be the two terms actually, x times a plus c, and the leftover b plus d. Those are our constants. Okay, now comparison would be easier now. What am I going to compare it to? I'm going to compare this numerator with the original equality, because we started with that. Denominators are exactly the same, the numerator must be the same. So that means the two x cubes must match. This must match up with this x cube. What does it tell me? It tells me the coefficient must match. So a must be equal to 1. So let me take away these boxes. So I can say a must equal 1. The second one, if I compare the x squares, I can say b must be equal to 1. If I compare the term containing x with this fraction doesn't have any x, so there is 0x. So I can say a plus c must be equal to 0, coefficient of x, there is no x. And if I compare the constants, b plus d must equal 1. So here, since I know a is 1, what is c? C must be negative 1. And since I know b is 1, d must be 0. So I found a, b, and c and d. It was quite easier this time. So this integral could be written as the integral of denominator x squared plus 1 dx plus the integral of denominator x squared plus 1 squared dx. The numerator of the first one is ax plus b, where we found a and b. A and b, they both were 1. So you would have 1x plus 1b. So these are both 1. So I found that is 1x plus 1, or x plus 1. And for the cx plus d, we found that c is negative 1 and d was 0. So you have negative x. Okay. So now, how do we find the integral of these two? Again, the first integral, if you remember, this is similar to what we did above. You have x squared plus 1 squared. So I'll try to break it up again. I will write it as x over x squared plus 1 dx plus 1 divided by x squared plus 1 squared dx. 1 squared or 1 is the same thing. I'm writing it in this way so you can see where I'm going with this. The other term, since the denominator is squared, I'm just going to keep it as it is. It requires a substitution. Negative x squared plus 1 squared. Okay, let's focus on the first integral. What would be this integral? If you pick substitution, if you let the denominator to be u, what do you get is for du, it would have 2x dx. But you have x dx, so there would be a missing 2. Okay, so if you go through the substitution, maybe I should write it. Okay, I'm going to write it down here just to make sure everyone knows. X over x squared plus 1 dx. I'm going to pick substitution u to be x squared plus 1, the denominator. Then du would be 2x dx. What is dx? It is du divided by 2x. So therefore this equals to x over u multiplied by, instead of dx, I have du over 2x. And these two can cancel out. So you would have 1/2 integral of 1 over u du, which is simply 1/2 ln absolute value of u. That is 1/2 ln absolute value of x squared plus 1. You may not need the absolute value since the inside is always positive, but I'm just going to keep it. So I found this first integral. It is 1/2 ln absolute value of x squared plus 1. After a lot of practice, you will notice that you don't really need to do all these substitution every time. You will see the patterns. How about the second one? The second integral is exactly the same as the tan inverse. So this is tan inverse of x, because a is simply given 1. And plus this third integral. How do you calculate that integral? You pick substitution again. We had negative x divided by x squared plus 1 squared dx. Same substitution, exactly the same thing. So if I pick u to be x squared plus 1, this would be u squared in the denominator. You still have negative x here. Instead of dx, you would have du divided by 2x. The x's will cancel out. This time you would have negative 1/2 integral of 1 over u squared du. And this is not ln. You should write this as u to the power negative 2 and use the reverse power rule. So it would be negative 1 over 2 u to the power negative 1 divided by negative 1 plus some constancy. You can cancel out these negatives. That is 1 over 2 times 1 over u plus some constancy. So this last integral becomes 1/2 times 1 over u plus some constancy. And u was simply x squared plus 1. So 1/2 1 over x squared plus 1. You notice that even when the powers are larger, when the denominators are quadratic, it was kind of easier to calculate a, b, and c, and d. But don't be fooled by this. It becomes more difficult if you have more powers or more combination. Maybe the very first example that we did was the most difficult one because it contained too many equations. But you notice that all follow the same structure. Okay, finally, after all this, these are the 4 cases that we're going to mention. We're not going to do the cubic power because factoring becomes an issue. So we stay as quadratic. So sometimes you notice the denominator contains, or the numerator contains a irrational factor. That means it involves square root or cube root or something. In those cases, not always, but most often, it is possible to pick that term as your substitution. What do I mean by that? It means if you look at this example, what you see is 2 square root of x plus 3 plus x dx, 1 over that dx. If you pick substitution and say let u equals 2 square root of x plus 3 plus x, then there is no way to actually simplify this fraction. This substitution will not work. But what if we pick the substitution instead of the whole thing? What if we only pick the square root and say the square root of x plus 3? The square root as the substitution as well. Would that work? Normally, when you take the derivatives, would cause some difficulties to calculate the derivative. So what you would do in these cases is you assume that I can get rid of the square root by squaring both sides. What would be u squared? U squared would be simply square both sides. You will get x plus 3. So now I would take the derivative. What would be the left side derivative? It would be 2u du. What would be the right side derivative? 1 dx. So I found out what is dx. Dx is simply 2u du. You don't need to always take the derivative with the square root involved. So you can kind of square both sides and take the derivative. That is the technique for rationalizing a term that contains square root. Again, not always going to work out, but if the trick is by doing that, then you can use this idea of squaring, or if it's cube, you cube the square root and take the root and take the derivative. What does this equation simplifies to? I would have 2, instead of square root of x plus 3, I have u. Instead of x, I don't know what x is. I can solve for it through this equation. It is u squared minus 3. This is exactly the same as x. So I will have u squared minus 3. And instead of dx, what do I have? I have 2u du. So I simplify this integral to something that doesn't contain square roots. I have 2u, and here du, and in the denominator we have u squared plus 2u minus 3. Now, if at this point they ask you to calculate this integral, you should be able to do that. First, you look at the denominator to see if you can factor it. We just talked about integration through a partial fraction. So you see if I can factor the denominator. And you notice you can do that by saying u plus 3, u minus 1, du. So I can write this integral as, actually let me write it down here. I can write this fraction as 2u divided by u plus 3 u minus 1 equals to something divided by u plus 3 plus another constant divided by u minus 1. And then if we go through a whole process of common denominator, we should have u plus 3 u minus 1 a times u minus 1 plus b times u plus 3. You'll end up finding a and b, which means you can split up that integral, that fraction, into 2 simpler fractions. Here I distribute these. I'll get au minus a plus bu plus 3b. And now I compare. Now I factor the terms that contain x. It would be a plus b. And the terms that are left over are minus a plus 3b. So now I compare these 2 sides of the fraction. This compare with the other side. Sorry, this is not supposed to be x. This is supposed to be eu. There's no x. Okay, so what do I get? Can I find a and b? Since left side is 2u, the right side should contains 2u as well. So a plus b must equal 2. And negative a plus 3b must be 0 because there is no constant on the left side. So here you can say that a equals negative 3b if you want. Sorry, positive 3b. You can solve for a and then replace it into this equation. You say 3b plus another b must equal 2. So I can find out what is b. B would be 1/2. And I can figure out what is a. A would be 3/2. Right, replacing it. Okay, you can check to see if it satisfies the equation, and it does. So I can say, okay, this integral could be simplified into sum of 2 fractions. One is where the denominator is 3/2 for a, u plus 3. And the other denominator, du, plus the other denominator was negative 1/2 or positive 1/2, u minus 1, d. And each integral can be calculated simply by doing a ln of u plus 3 plus 1/2 ln of u minus 1 plus some constancy. And at the end, we have to get rid of that u. What is u? U was square root of x plus 3, if you remember. We picked u to be square root of x plus 3. So I have square root of x plus 3 plus 3 and plus 1/2 ln absolute value of square root of x plus 3 minus 1 plus c. And this is the answer. We got rid of all those u values. Again, one thing that you should notice is that this, I skipped actually some steps because we assumed that we already know this integration. You can always take the 1/2 out. You can always put the 3/2 outside and take the integral. So first I recommend you guys to try to do substitutions for the simple cases. Make sure that you know how to calculate these integrals. The more comfortable you become with these fractions, the easier it becomes to calculate the more difficult ones. Okay, this is, I think, already too much, so I'm going to stop at this point. This is the end of 7.4.